Start? Yeah? Alright. So hi everyone. Thanks a lot for coming to the holography session with four wonderful talks. So yeah, we start with Alexander Tyukov from local.
Okay, thanks. First of all, let me thank the organizers for putting together this great conference and for giving me the opportunity to present my work. Today I'm going to tell you about the new method, which is based on the supergravity, to compute the 4-point correlators in the n equals 4 superior Mills theory in 4 dimensions, based on the so-called bubbling geometries in AdS5. This work was done in collaboration with David Turton, who is here in the audience. So as an introduction, let me give you some brief motivation why we're interested in the computation of the 4-point functions. So probably the 4-point functions has been the most studied object in the holography since the very beginning. And the reasons are following. First of all, the 4-point functions are fully dynamical objects, which are not completely fixed by the conformal symmetry. So they contain the information about the interactions in the theory. They're also not subject to the non-renormalization theorems, which are coming from the supersymmetry, so they depend on the coupling of the theory. And if we manage to somehow compute those correlators, we can use them to extract the information about the strongly coupled CFT. In particular, if we do the double OP expansion of the 4-point correlators, we can extract the anomalous dimensions of the exchanged operators. And that's very important information. And as you all know, the standard holographic technique to compute such correlators is to use the Witten diagrams in the bulk. However, in spite of the development of the holography, there are still some theories for which all 3-point and 4-point couplings of the bulk fields are not known. And such particular example includes the 2B theory, compactified on AdS3 times S3 times T4, which is dual to the famous D1, D5 CFT. And this theory is particularly important because it's related to the microstates of the black holes. But I'm not going to talk about this in this presentation. And therefore, it's important to develop some alternative techniques that bypass the use of Witten diagrams. And such new method was originally invented in the context of AdS3 CFT2 holography, and it was used to compute the whole range of correlators, which involve both heavy light correlators and all light. And here is the list of people who were actively involved in developing this method over the years. In today's talk, I'm going to take a step further and to develop the similar technique for the higher dimensional case of the holography. So I'm going to be focusing on the most studied case, the string theory on AdS5 times S5, which is dual to n equals 4 superior Mills in 4 dimensions. And I'm going to be working in the supergravity approximation, which means that my results will capture the leading order behavior in 1 over n and 1 over lambda. In particular, I'll be focusing on the half BPS sector of this theory. As you know, n equals 4 superior Mills contains 6 scalars in the adjoint representation of the gauge group. And out of these 6 scalars, I'll be interested in only into phi1 and phi2, from which I'm forming the holomorphic combination that I'm calling Z, and their conjugates. And the single trace chiroprimary operators in this theory are simply given by the trace of the powers of Z to the power n, which has to be greater than 2 because we're working with the gauge group SUN, not UN. These chiroprimaries have their conformal dimension delta equals to the particular U1 R charge that I'm calling J. And what's remarkable that these chiroprimaries are in one-to-one correspondence with the supergravity fluctuations on top of AdS5 times S5 that were classified in this paper almost 40 years ago, so long before the invention of the holography. So the idea of the method that I'm going to present you is following. Instead of computing the 4-point function of the correlators in the vacuum, I'm going to replace this with a computation of the 2-point functions in the non-trivial heavy state, which is dual to some supergravity background. So this heavy state will be, as I will show you later, will be created in general by multi-traces or multi-trace operators, which we consider to be heavy. And the light fluctuations on top of this geometry will be dual to the light fields in the bulk, non-backcreated fields in the bulk. And the operators will be descendants of these chiroprimaries. So first, I will tell you how one can use the standard holographic prescription to compute the heavy light-light correlator, and then I will tell you about the specific limit in which one can obtain the correlator for light fields. So as the background, I'm going to consider the famous LLM geometry obtained by Lin, Lunin, and Moldesena. This geometry is a solution of the 2B supergravity, which contains only the metric and the 5-form flux. It has 16 supercharges, and it also has SO4 times SO4 symmetry. So this solution depends essentially on one scalar function, z, which is related to the vector potential v. And this scalar function z satisfies the homogeneous 6-dimensional Laplacian. So this solution is smooth, and that imposes the certain boundary condition on the plane y equals 0. The condition is such that z can take values plus and minus 1/2 on this plane, and that physically determines which one of these two S3 spheres shrink smoothly. So this boundary condition can be graphically depicted in the coloring of x1, x2 plane into black and white regions. So now let me show you the geometry that I'm going to consider. So we're going to consider the geometry which has the same topology as the vacuum diagram, which is simply the black disk. And we take the small deformation of this boundary given by this equation in the polar coordinates. So this deformation was previously called the ripple deformation. It depends on two parameters, alpha and n. Alpha controls the size of the fluctuation, and the n is the frequency. And so you can see that for higher n, this really looks like a ripple on top of the black disk. But in this work, I will concentrate on the middle case, n equals 2. And physically speaking, if you are in the black region, you are sitting in the middle of the AdS5 space, where one of the circle S3 inside of AdS5 shrinks, and outside in the white region, the other circle, which is the part of S5, shrinks smoothly. So the holography of this geometry was considered in this paper by Skenderis and Taylor in 2007, and what they found that this ripple deformation is dual to some coherent superposition of the states, which are created both by single and multi-trace operators. So this state is parameterized by the same parameter alpha which I showed you on the previous slide. At the moment, this state is not fully holographically known, but we know this state perturbatively in powers of alpha. And in the first order in alpha, this state is simply created by trace operator trace z square. In the second order, there is in principle the mixture of the double trace operator, trace z square square, and the single trace z to the 4. But this ambiguity will not play any role in what I'm going to tell you. The energy of this solution and its R charge were also computed in this paper, and they're proportional to the central charge of the theory, which is n square over 4. And what you can see from this formula is that if alpha is small but independent of n, the state has the same conformal dimension as the central charge, so it can be called perturbatively heavy. And if you interpolate alpha all the way to 1 over n, this state will become light, and it has just a dimension of order 1.
What is A? What is capital A?
Capital A is some unfixed parameter that determines the mixture between double traces and single traces in the higher order, but as I said, it's not going to be relevant for the purpose of this talk. So at the 0 order in alpha, the geometry simply reduces to the vacuum AdS5 times S5. One of the S3s becomes the part of S5, and another one becomes the part of AdS5. And in the first order in alpha, we expect that this geometry is dual to the supergraviton in the bulk. And these fluctuations, as I mentioned, were classified before on top of AdS5 times S5. However, it's very important to bring this LLM metric into the right gauge. And the right gauge is the known de Donda-Lorentz gauge, which completely fixes the diffeomorphisms in the bulk. So the resulting metric will not contain any gauge degrees of freedom. So if we manage to bring the metric in this form, we will be working only with the physical degrees of freedom encoded in the bulk solution. So luckily for us, this work has been done already, and such transformation was found. What's important is that both metric and the phi form can be written in terms of the fluctuations, or in terms of the two fields, Sn and Yn, which are the eigenfunctions of the scalar Laplacians on AdS5 and S5, respectively. And these 5-dimensional fields Sn are precisely dual to the chiroprimary operators On that I showed you before. And in the second order, we would like to play the same game and make our life easier by bringing the metric into the Lorentz gauge. However, in this case, we will have to do all the work. I'm not going to show you the details, but this calculation can be done. And the metric in the second order in alpha can be brought to the de Donda-Lorentz gauge. However, the expressions for the metric components are too complicated to present it on one slide. But anyway, they're still very convenient to find the two-point function of the probe field on top of this geometry. So now let me tell you about the probe field. So we're going to take the x-dilaton, which satisfies the most simple equation of motion in the bulk, which is box 10 on phi equals 0. So it's a non-back-reacted field. And I'm going to expand both box 10 and phi in orders of alpha. So this essentially reorganizes this equation of motion into the system. into the system of equations. So at the zero order, we have to solve just for phi 0. Then we can use this solution, which becomes the source for phi 1. And then, having found phi 1, we can use it as a source to determine phi 2. And since we're working with the perturbations on top of S5, it's convenient to express the fluctuations into the spherical harmonics, which gives the corresponding expansion for the coefficients B. Since we are working with the second order equations, we need to specify two boundary conditions for this field. So first, we impose the smoothness of on the field phi in the interior. And second, we use the standard holographic prescription at large R. So we expand this field near the boundary. And the first non-normalizable mode is dual to the source at the boundary, which we put at some point n on the cylinder. Then the normalizable mode will encode the two-point function of the probe field in this geometry. And eventually, we're after this coefficient B1 of x, which encodes the information of the heavy light-light correlator of interest. Okay, so now let me specify the particular operators that we're going to consider. We're going to take the descendants of the antichiral primary, which we're calling dk. So this operator has the conformal dimension k plus 4 and r charge minus k. So these quantum numbers are essentially encoded in the lowest spherical harmonic on S5. So then we can find the solution for phi 0, which is simply given by the bulk to boundary propagator, k delta, from point x to point n on the boundary. And then we can use this solution to determine phi 1 and phi 2. And the correlator will be encoded in this coefficient bi of x. So if you expand the coherent state H, which I showed you before, in the powers of alpha, you will find that at the second order in alpha, this heavy light-light correlator is simply proportional to the correlator of 4 light fields with the coefficient alpha square. And this is the promised the light limit. So let me briefly tell you how one can do this. So we need to solve for phi 2 in the 5 dimensions. And for that, we need to project our sources to the given spherical harmonic and integrate them over the S5. That reduces this equation to fully 5-dimensional equation, which can be inverted using the standard Green's function. So to make the comparison of the 4-point correlator with the results in the literature, it's very convenient to express the answer in terms of standard D functions that usually appear in this business. To do that, we have to go from the global coordinates to the Euclidean Poincare coordinates, in which the bulk boundary propagator is given by this expression. And if we manage to rewrite our projected sources in terms of the product of 3 bulk to boundary propagators, then we can get the 4th propagator simply by inverting the box on B4, and that will give us the 4th bulk to boundary propagators. Therefore, the whole solution will be expressed in terms of D functions, which are given here. So it's easy to say, but not so easy to do. However, we have managed to succeed and found the expression for the 4-point correlator in terms of the D functions in the position space. But because D functions satisfy lots of algebraic identities between each other, the answer in the position space is not unique. And it's much more convenient to transform the result in the position space into the Merlin space. So for that, we need to strip off the kinematic factors, which depend on the conformal dimensions of the operators we're taking here, such that the stripped correlator will be functions only of the conformal cross ratios, U and V. Then we can apply the standard formula for the Merlin transform, which will give us the Merlin amplitude as a function of the Mandelstam variables S and T. Thanks. Okay, so this is the result for the correlator of two chiroprimaries, O2, O2, and two descendants, dk and its conjugate. So this Merlin amplitude has the correct pole structure, so it has only simple poles at s equals 2 and u equals k plus 4. And it also has the correct flat limit when Mandelstam variables are taken to infinity. So the only unfixed part of this correlator is some numerical factor which can only be the function of the parameter k. And I'm going to tell you how one can fix this. So to fix this normalization, we would like to compare this result, this supergravity result, to the 4-point correlator of 4 chiroprimaries of the dimension 2 and k plus 2. So this correlator has been computed in many different ways in the literature, and it's completely known. So the stripped correlator depends, it factorizes into the product of some quadratic function of u and v, which comes from the solution of the superconformal word identity, and some function that I'm calling curly h, which for this dimension is given here. So to make the comparison, we need to act on this correlator with a differential operator which corresponds to superconformal word identity. And essentially, this operator is the square of this operator delta 2, which was found in the literature. So if we do this in the position space, we have to convert the result back to the Merlin space. And then we can compare the residues of this Merlin transform, for example, at the pole s equals 2. And that essentially fixes the entire normalization for the correlator. So once we fix the residue at one of the poles, the rest of the correlator will match. And that essentially proves that our supergravity method is capable of capturing the entire correlator, not just some channels. Thanks. So, okay, let me briefly summarize my talk. So in this talk, I showed you how one can use the new supergravity technique, which bypasses using written diagrams in the bulk and is based on the solution of the equations of motion in the non-trivial supergravity background. So we computed the 4-point correlator of 2 chiroprimaries and 2 descendants, which we related to the 4-point function of chiroprimaries using the superconformal word identity. And in terms of future directions, it will be interesting to generalize this technique and replace the single trace operator O2 with more generic operator ON, which is possible in our approach, and will correspond to considering the higher modes of the high harmonics of the Riplon. And speaking about the talk that you've heard on Tuesday by Rodolfo Russo, it is also interesting to use our technique to compute the correlators which involve the multi-trace operators, which are powers of the single trace operators OM. And I'm going to finish with this. So thank you very much for listening.
In one of your slides, the 4-point function was proportional to a function of k.
Say again?
The 4-point function m,
Yes.
Pascal m, was proportional.
This
yeah,
one?
Yeah.
Okay.
Is it possible to fix the numerical coefficient by using unitarity of the S matrix?
Unitarity of the S matrix. Well,
Or some
the unitarity is already encoded in this correlator. So it's just a numeric coefficient which depends on k. So it's not.
Okay, I have another question about the dilaton perturbation, that you wanted it to be smooth in the interior.
Yes, that's right.
Can't you have a dilaton that goes to minus infinity that corresponds to asymptotically weak coupling?
Not in this geometry, because we take the smooth geometry. So all the solutions on top of all the fluctuations on top of this geometry has to be smooth. So it's important to consider the dilaton that doesn't blow up in the interior.
Did I understand correctly that you computed from this heavy light construction, that you computed the correlator not of the superprimaries but of some descendants?
Yes. So the dilaton is dual to the descendant.
And then you use the superconformal word identities
of
to
the
reconstruct.
Mm-hmm.
And then you reconstruct
yes,
the correlator of.
We didn't reconstruct, but we did the opposite. We took the known result for the chiroprimaries, and then we acted with a differential operator to match it with our supergravity calculation. But in principle, this method can be reversed, and based on the correlator of the descendants, one can reconstruct the correlator of the chiroprimaries.
But there is a differential operator involved. Are you not worried about? There is a free part of the correlator which also contributes.
Yes, in this approach, we're not considering the free part, because the free part corresponds to the G and Mills equals 0, and in the supergravity, we are working in the opposite regime of the large toothed coupling. So we are capturing only the interacting part of the correlator. So we are dropping the free part.
Okay, you can't reconstruct that because it's
not with this technique.
I see. Thanks.
Maybe I can ask something.
Sure.
So you're saying that the method you use is simpler than using Witten diagrams?
Well, it's not simpler, but it depends what you mean by simpler. But for some theories, like I showed on the first slide, the 4-point Witten diagrams have never been computed and fully understood. So one has to invent some alternative techniques which bypasses.
But is there a technical difficulty? I mean,
once
you would expect the two things to be equivalent at some level. So.
Yes, of course, it's equivalent in a sense that you take two of your operators and you back react them in the bulk, and that creates some non-trivial geometry. So in this sense, it's equivalent to using Witten diagrams.
I see, but so
the advantage is that if we know the exact solution of some theory, but we don't know the Witten diagram, then this is the only method which can produce the 4-point correlators.
all right, thanks. I don't know actually what. Thanks. Okay, so now we have